Well, dear, welcome back. So, please wear a mask because this will save you from the dangerous coronavirus. Always put your mask whenever you are going out. With this message, let us continue our discussion. And today, now we are in a position to tell you the most interesting part of our fuzzy logic: how to capture human knowledge using whatever we have studied so far, and with the help of fuzzy rules. Okay. Actually, this is very interesting, right? And because we are thinking that we should capture the knowledge of a farmer who has a lot of wisdom and experience, or a medical professional who has a lot of knowledge and experience in her or his domain. So that's all we are trying to do in a fuzzy framework, right? So today we are going to discuss that how uh, human knowledge can be captured using fuzzy rules. In 1973, Lecture-4, that is, he is the father of modern fuzzy logic, he wrote the second most influential paper, and there he proposed that we can write if-then rules, okay, to capture the the knowledge from the expert. So the architecture of the rule is like this. It has two parts. One is called if. See very carefully. If X is A is a fuzzy set. X is any element in the universe of discourse. So this is called antecedent. If this, then that. If humidity, then there will be rain. If for example, uh, wind speed is high, then selling will be easier. All kind of, so these are linguistic um, representation of knowledge, right? So you see, rule has two parts: antecedent, consequent. If this, then this. Now, in fuzzy form, you see X and Y. If X is A, then Y is B. This simplest rule. We will also discuss how we can um, design more complicated, complex rule which has better expressive power. But start from the simple one. Here, X and Y are the linguistic variables. A and B are linguistic value determined by fuzzy set in the universal discourse X and Y respectively. So linguistic values, okay, how you will get defining a membership function, having a membership value, and seeing where in the universal discourse the variable X and Y belongs. Okay, sorry. Now let us see, consider a monotonic selection. Okay, what it is a jargon term. I will tell you. Very simple. Say this is my fuzzified height. Okay, so this is a fuzzy function, continuous fuzzy function, and I have captured height of a person with this fuzzy function. And this is, say for example, weight, another variable that I have fuzzified, okay, in this form. Now, monotonic selection means that you see these two attribute, height and weight, we are assuming that they have linear um, relation. For example, if my height is bigger, I will be heavier, and which not always may not be true, but this is my assumption. We are trying to understand that how fuzzy rules can infer something, right? You see, even this kind of simple fuzzy rule, if I write, you see, if height is tall, then weight is heavy. Okay, so you see now how I will generate that. If the height is tall, right? So I will use that. So one person will come and it's based on possibility theory. So I will measure her height and then I will put it in my membership function. In this universal discourse, I put that element. It's a crisp element, right? Somebody has come with some height, say 185 centimeter, and then with a membership value this, okay, in top height, and then I will project this on my and I need to know. For example, somebody asked me, okay, my height is this. Can you just guess, most logical guess, that what will be my weight? Okay, so I will do like this. So I will project this. Okay, and this is my membership uh, function, which is capturing weight, and whoever is coming over here. So this I will measure. This is a crisp value again. I am getting from the fuzzy, say. So whatever will be the value, say 76 kg or whatever, right? So I will tell you that, okay, if your height is this, then your weight is this. If your height is this, then your weight is this much. If your height is this, then your weight is this much. So this is a simple example that how writing if and then rule. Just I have I have written, if the height is tall, then weight is heavy. Only this is the thing which I have proposed, and I am evaluating this after fuzzifying tall and weight in this form. I could evaluate that what could be, or other way around. Say if somebody has come with 80 kg weight, and then what will be her height? I just tell from here. So this will be her height. You got it? So we write rule show that it can infer something. Okay, this is an example. Now, in a full-blown form, we will discuss that how whatever knowledge we have gathered so far can be utilized for designing a fuzzy expert system. It will be an intelligent system which will actually make some logical inferences. Okay, there are two approaches very famous. One is Mandani approach. Another is called Shiguno approach. Okay, and they are a little bit they are similarity. Only one difference is there. So this is just a history. Abraham Mandani in 1975, okay, of London University, built one first fuzzy system to control a steam engine and boiler combination. So using his um, system, we will also design an expert system using Mandani's approach. Okay, and on the other hand, Shiguno is a Japanese scientist, suggested to use a single spike or a singleton membership function. Actually, he used singleton membership function show that um, the the defuzzification becomes simpler, and computation in the entire process becomes much more less than the Mandani approach. Otherwise, there are a lot of similarities. So we'll one by one we'll study in depth. Okay, first Mandani approach, and I already have decided that Mandani approach using some available expert system, fuzzy expert system tool, I will design one inference system using Mandani approach as well as Shiguno approach, so that you can see that similarity and how easy and how difficult they are. Okay. So first Mandani approach. Okay. So here these are the rules, right? So you have some say crisp input variables. It could be anything, height, weight, this, that. Okay. So those are crisp parameters. You need to first fuzzify them, because unless you fuzzify, you cannot write fuzzy rules, and fuzzy rules are the forum where you are actually uh, encoding the expert's knowledge. So first you will have to fuzzify the crisp input. But first, of course, you will have to understand the problem, and you will have to decide what will be my input, what will be my output. So if this is the input, so how I will fuzzify them. So first fuzzification of the input, and then you will have to write the rules explicitly. Okay, and then you will have to fire the rules. That is, we call inference engine, or whatever this jargon term. Basically, rules are executed, and what the execution of the rule means, we'll discuss. Okay, it's nothing but whatever you have studied, fuzzy set intersection or union or like that. Okay, simple things. So fuzzy evaluation, then aggregation of the rule output, and then that is what the result we have got from the expert system. But again, we need to de-fuzzify so that we need a crisp value. We are dealing with crisp value only because fuzzified output will not make any sense. Okay. So in that sense, fuzzy is actually an operator. Logarithm you have studied. By the way, this is a very good example. So when there was no calculator, computer, people used to use physicists used to make their calculation using log, right? So what logarithm is doing? It is converting your cumbersome multiplication, division in the form of addition and subtraction. But in the log domain, if you just have an expression with very ugly, for example, multiplication, division. So what you do? You take log. And the moment you do take log, and then that multiplication, subtraction, division is converted into a addition, subtraction. And normally it is easier to operate in addition subtraction domain rather than making multiplication. So you do whatever you want to do in addition subtraction domain. But this is not the real domain, right? You have taken the log. So with the result, what we do? We take anti-log. In case of signal transformation also, Laplace transformation and the inverse Laplace transformation. So here also you have fuzzify. So if you think fuzzy as an operator, right, as a transformer, then fuzzification, after that you need to defuzzify, right? After fuzzifying, you need to defuzzify. So these are the 4 steps which we should follow. Now with a concrete example, say I have 3 fuzzy function A1, A2, A3. They could be simply, as we discussed earlier, they could represent short height. Okay, this is average height, this is tall. Okay, and this could also represent your weight. Okay, this is less weight, this is heavy weight, kind of thing. Anything, right? These are the 2 fuzzy set. These are the 3 fuzzy set, and we have crisp input, say x1 and y1. Okay, so x1, this is value in the universal discourse has membership value 0.2 in the fuzzy set A1. Okay, no, sorry, in the fuzzy set A2 it is having value of 0.2. In A1 it has a value of 0.5. And similarly, membership value of B, since the functions are known, B in B1 equal to 0.1. Okay, and in B2, you see the same point B2, it is a value of 0.7. Now, I'll have to make the rules, okay, and evaluate them. So fuzzy rules are evaluated using operator like OR operator or union operator, you can call, okay, where the 2 fuzzy set, we are doing union operation, we are doing intersection operation. These are the 2 very common kernel you can see of computation in fuzzy logic, right? And by the time you know that fuzzy set is a tuple where every element is coupled with membership value. Okay, so if the set is there, then you can do union, intersection, all kind of thing, inversion, right? So here, these are the 2 very important operators which we'll use. You see, now I am writing the rule. Rule number 1: if x is in A3, that is, so just take a new example. I have taken an example. Say x1 is a crisp. Now it is in fuzzified because A3 is value 0, or y is in B1 with a value 0.1, then z is, the output is C1 0.1. So what does it mean? You see, I have input variable x1. For that, I have a membership function like this. I have another input y1 crisp input, and I have fuzzified them by a membership function like this. Okay, and then I am writing a rule. If x is this, okay, with a value actually, or y is this, or means, or operator means union, okay. So the maximum of the value, this one 0, and this one I am projecting it, injecting it, and this is my output. In output, what provision I have made? I have made 1, 2, 3, 3 fuzzy function. Okay, so this is actually giving me the shaded area is the output in fuzzy form when one rule is fired. So this is jargon term. I am calling when I am writing this rule, if x is a3 with this value or y is b1 with this value, then z is c1. So this is very linguistically I am writing the rule, if then rule, right? If this and the, so you see earlier we wrote this if then. Then with or I am complicating, and actually in real life these are the kind of rule which is more useful. So if x is this or y is this and say another z is this or this is this, rule can be bigger. Okay, so if the more number of inputs are there for a complicated prediction, it could be more inputs, right? More attribute. If the crop yield of the good yield of the crop, for example, is depend on many factors. If the rain is good, then if there is no storm, and there is no storm, and there is no insects, all kind of thing, right? The wisdom of the farmer, then crop will be good. So is this type of rule I can also capture. So this is a simple example I have given. Example. Okay. So if this rule is fired, that means rule is evaluated by OR, I am getting simply a shaded area. Similarly, when another rule, if x is in A2, the same thing, you understand, right? So this is my, that's example I am giving. This is my triangular membership function. This is my some trapezoidal kind of thing, truncated trapezoidal membership function. And then I am writing rule. If x is A2 with this value, and then if x is this, y is this, then z is this. Okay, see here. So since AND operator is there, so minimum of these two will be fired. So 0.7 and 0.2. Who will produce? So here there is an AND operator. Okay, so who will go out from here? From an operator minimum, right? Minimum value 0.2. So 0.2 is actually clipping the second membership function which I have made available to accommodate my second rule. So I will get this shaded area as rule number 2 is fired. Then say I am writing another rule. If x is a 1 with a value 0.5, then z is C3. So there is no AND also, just like earlier, height and weight, I just projected it to get this third output. So as many rules I will write, that many shaded area means you see output in the form of area I will find. And we need to aggregate them to have, when all the rules are fired, this is my output, which will be aggregation of this. But I will tell you, see, look here carefully and see the way I have allowed my operator to function or and on the accommodative. So this is my defined membership function, right, in the output. So the way I have done it, just it is simply clipping, as if it is clipping the area under the curve, which is my membership function. Okay. So there are, can you do better? You see, there are two actually concepts, right? So one is called clipping, another is scaling. See, all the examples which I have given here, they are actually just clipping the output and giving the result. Okay. But in doing so, it might be incurring some error, and it might be unnecessary. You see, when when this rule is fired, I am assuming that this is my trapezoidal membership function. So I assume the base of the trapezoidal function to be taken into consideration. But I did not redesign. You see, only 0.2 is being fired, right? So I would have redesigned within this domain this membership function. Then you see, then by firing the rule, I could have got this area. And since I have assumed that trapezoidal membership function is the best one, so why not to redesign the trapezoid in this domain for which you are firing? So this concept is called scaling. And you see, in doing so, what you have done? You have just erased these unnecessary areas, right? Unnecessary areas are no more there in your computation. So this is the smaller area now, which is more logical. When this rule is fired, this is the output which you should have got. Similarly here, you see, I could have easily eliminated that part. Have you understood? Then here also, you see, I could redesign. This could have been my membership, and this would have been done. So I can always save computation, be more logical if I do scaling type of rule firing. You understand? Clipping and scaling. Clipping is easy, more computation, more unnecessary things are there in your output, not very precise, not very good. Scaling is actually you need to do some extra work to scale down the membership function in that particular domain where the rule is being fired and reconstruct the membership function, right? So in doing so, you are achieving something. What is it? You are achieving preciseness. Okay. So as I am telling now, so these three rules have been fired. Three rules have been fired, and there are three. So we can aggregate them. This one, this one, this one. So after aggregation, so this is my total output after rule is being fired. Okay. But what I will do with this output, I cannot figure out anything because this is again in the fuzzified form. So I need to have some crisp value. So you see, what if I could calculate the? There are so many methods, and I will discuss in detail, little bit detail, that where is the centroid of this area? Okay, or if I consider as a fictitious mass, so where is the center of gravity? Had it been a kind of mass? So can I calculate the centroid of this shaded area? Can I calculate center of gravity of this mass? That could actually be the resultant of this area. Okay? So that is called DeFuzzyification, because this output is in fuzzified form, which is not very useful. So we need to defuzzify. So this is the fourth process of Mandani inference. So we'll discuss this in the next class. Till then, stay safe and stay tuned. Again, so I'm leaving, wearing a mask. So if you have any question, this is very, very simple, interesting, very elegant, and very not so simple. When I will design a inference system, you will see how laborious it is. But idea is very simple. Okay, so that's why I love it. So I need to talk a little bit more. That's why I'm stopping here about detail about defuzzification techniques, several defuzzification techniques, before I am I can take an concrete example. Till then, stay safe. Have a nice day. Bye bye.